Welcome to our presentation on advancing robotics development with neural dynamics in Newton. Today, we'll be exploring neural robot dynamics, or NeRD, a groundbreaking research initiative from NVIDIA that's redefining how we simulate and train robotic systems. Let's begin with the executive summary. The fundamental challenge we face is that classical analytic dynamics models simply cannot capture the full complexity of modern robotic systems. Our solution is neural robot dynamics, a neural simulation framework that learns robot dynamics directly from data. The key innovation here is a drop-in replacement for traditional physics solvers in engines like Newton, enabling more accurate and adaptable robot simulations. The impact? This approach fundamentally bridges the sim-to-real gap, allowing robots to learn complex tasks and continuously improve through real-world experience. So, what's wrong with traditional robot simulation? Classical analytic dynamics face several critical limitations. First, they oversimplify contact physics. Traditional models cannot accurately capture complex contact-rich interactions, which causes failures in real-world scenarios. Second, they omit kinematic loops, missing closed-chain mechanisms and providing incomplete representations of robot structures. Third, these models are non-differentiable. They cannot be easily optimized, have limited ability to learn from data, and are difficult to fine-tune for specific robots. The bottom line is clear. Modern robotics requires capabilities that classical physics engines simply cannot provide. This brings us to NeRD, the Neural Robot Dynamics Framework. NeRD is a learned neural simulation framework that predicts future states of articulated rigid bodies, that is, robots with multiple joints, in contact with their environment. Its key capabilities include making stable and accurate predictions over hundreds to thousands of simulation steps, generalizing across different tasks, environments, and low-level controllers, and most importantly, being fine-tunable from real-world data to bridge sim-to-real gaps. The unique feature? It serves as a drop-in replacement for analytic solvers, working seamlessly with existing robotics frameworks without requiring massive infrastructure changes. NeRD addresses these challenges through three core advantages. First, it provides expressive, differentiable models that predict stable states over long horizons, can be optimized end-to-end, and learn complex dynamics patterns. Second, it captures complex contact-rich physics, modeling realistic contact interactions, handling multi-contact scenarios, and proving more accurate than simplified analytic models. Third, and perhaps most importantly, NeRD generalizes and adapts. It works across different tasks and environments, narrows the sim-to-real gap, and can be fine-tuned on real-world data as robots gain experience. How does NeRD compare to traditional simulators? The key differentiator is our hybrid approach. Traditional neural simulators tend to be task-specific, overfit to training scenarios, and have limited generalization. In contrast, NeRD takes a task-agnostic training approach with a hybrid analytical plus neural architecture. It serves as a drop-in backend for physics engines and can reuse existing policy learning environments. The activation is remarkably simple, just one-line switch to enable NeRD as your physics backend. Let's examine a side-by-side comparison. Classical analytic dynamics excel in simple scenario speed and have interpretable equations, but they struggle with complex contact modeling, are non-differentiable, cannot learn from data, and maintain a large sim-to-real gap. NeRD, on the other hand, while potentially slower in simple scenarios and operating as somewhat of a black box, provides accurate complex contact modeling, is differentiable end-to-end, learns from data, and significantly reduces the sim-to-real gap. The key insight is that NeRD provides accuracy and adaptability where classical methods fall short, though it does require initial training investment. Our vision for the future of robotic simulation involves a continuous learning lifecycle. In Phase 1, each robot is equipped with a neural dynamics model pre-trained from analytical simulations to capture baseline behavior. In Phase 2, the model continuously fine-tunes as the robot operates, accounting for wear and tear and adapting to environmental changes. In Phase 3, we achieve hybrid simulation with neural dynamics for the robot and analytical dynamics for the environment, creating a digital twin. The result? A continuously improved simulator that enables learning of versatile robotic skills.
Let's dive into how neural robot dynamics works technically. The first key innovation is our hybrid prediction framework, which replaces time integration in traditional simulators. It combines analytical collision detection with learned models and leverages intermediate simulation quantities, like robot state, contact information, and joint space torques. The advantage, this approach generalizes regardless of task, scene, or controller. The second innovation is robot-centric input parameterization, where all inputs are transformed to the robot's base frame. This enables reliable predictions at unseen spatial locations and enhances long-horizon accuracy. The architecture maintains compatibility with existing simulation frameworks while replacing the physics solver. Training NeRD models follows a task-agnostic approach. We generate data sets of 100,000 random trajectories per robot, with each trajectory spanning 100 time steps. These include randomized initial robot states, joint torque sequences within motor limits, and optional environment configurations. Our network architecture uses a causal transformer based on lightweight GPT-2, taking simulation states from the most recent 10 steps as input. Importantly, training can source data from any simulator, whether Newton, MuJoCo, or others. Thank you for your attention. We now open the floor for questions. Key discussion topics might include how NeRD compares to other neural simulation approaches, computational requirements for training, handling of soft robots or deformable objects, real-world data needs for fine-tuning, development roadmap, integration with existing RL frameworks, and licensing terms for commercial use. Thank you for your interest in neural robot dynamics, and stay tuned for training and inference code releases.